Now we're going to look at the net change as the integral of a rate. When we talk about a rate, of course, it's going to be a rate based on time. So now we're going to be looking at, again, an interval, but this time our interval is going to be from time 1 to time 2. And it's going to be, the net change is going to be based on your function s of t, so it's in terms of time. For example, if we have the integral, for this case here, it tells us the water flow into an empty reservoir at a rate of 3,000 plus 20t liters per hour. So this is a rate. What is the quantity? We want the quantity of water in the reservoir after 5 hours. So the integral, as we can see up here, is from time 1 to time 2 of the rate of change. So the function with respect to time. So here's our function with respect to time, our rate function, from 0 to 5 hours. What we need to figure out is the net change, and basically how much water, the quantity of water that is actually in the reservoir after 5 hours. So we start off with our integral as a rate of change. Now this is our rate of change function with respect to time from 0 to 5 hours. We then can take the integral of this, which we know is going to be 3,000 t plus 20t squared all over 2, evaluated from 0 to 5. Now we know that it goes from 0 to 5. That means we can then say 3,000 times by 5 plus, this becomes just 10 times 5 squared, subtract, again, 3,000 times by 0 minus 10 times 0 squared, which we know just becomes 0 as a whole. So then if we multiply this out, we'll get 25 times that, so you get this. Now what this actually is, that's our net change over our times, which, so after the last over 5 hours, we have a quantity of water, and it's liters per hour, so this would be then your liters. So in the reservoir, after 5 hours, we would have 15,250 liters in the reservoir. Now another thing that we will see a lot of is going from velocity to distance or acceleration to velocity. When we take the integral of velocity, we actually find the distance. Now there's two ways that we have to look at this. The displacement during the time period and also the distance traveled during the time period. And then if we have acceleration and we take the integral of acceleration, we get the velocity. Both of them are rates of change with respect to time. So we have this initial time and an ending time for both of these. Now displacement just means between time 1 and time 2, how far do you go away from where you're initially starting? That's your displacement. Now your distance traveled, you could actually go back and forth, back and forth, back and forth, and your displacement will only be a certain amount, but the actual distance traveled is the absolute value of each of these. So we'll look at how you can calculate each of these differently. We'll look at this particular example. So we're going to find in both of these ones the displacement and the distance traveled from 0 to 10 for your time of a particle that moves in a straight line with a given velocity, with the function here. So if we look at our displacement versus our distance traveled, we have to set up both of our integrals from 0 to 10, because that's our interval that we're working with. They give us the velocity function, so 36 minus 24t plus 3t squared, whereas distance traveled is going to be the absolute value of this. So let's look at the displacement first, just so we're not involving the absolute values. If we have to take the integral of this, we now know that we can say it's going to be 36t minus 24t squared over 2 plus 3t cubed over 3 evaluated from 0 to 10. And we've got some things that will cancel out. So we'll have 36 times 10 minus 12 times 10 squared plus 10 cubed, and that whole thing again subtract the scenario where you have 0. Which we know is just going to become 0. So plugging everything in, we're going to find that we get 160. Now, let's just assume here that our velocity is in terms of meters per second. So time is in seconds, and your distance is in meters. Then we have 160 meters for our displacement from where we start and where we end in the 10 seconds. Now we want to look at our distance traveled. So I'm just going to erase this so we have a bit more room. And we'll just put a little note here that's minus 0 because it cancels out. So here we need to look at this one a little bit more in detail in terms of how we can figure out the absolute value of this. So if we actually look at the function itself and we factor it, so the integral from 0 to 10, and we're going to take the absolute value, we can factor out a 3, and we have t squared minus 8t plus 12 dt. And we take the integral and we just, till 10. The absolute value of 3, and we factor this, we get negative 6 and t minus 2. The graph for this is going to be a parabola that has roots at 2 and 6. And it's opening upwards and it's stretched by a factor of 3. We have this sort of graph. Now what it's actually asking us for is the area under the curve, so the integral here, the area here, here, and here. But here you can see you have a negative area. So by taking the absolute value, we're actually looking at this little region. So the distance traveled here, here, and here. So we need to split our integral up to showcase this a little bit better. So what I've written here, just as a little side note, for the integral from 0 to 10 of this whole function, which is our velocity function with respect to time, we can split it up from 0 to 2, which is this integral here, which is positive. And if we subtract off the negative component, it actually makes it add. And then we add from 6 to 10. So we're going to actually evaluate the integral 3 times based on the roots of the actual function that we're working with. So we have to evaluate this. We have to evaluate this and evaluate this to find the total distance traveled, not the displacement, not from where it starts and ends, but the actual forward, backward movement, total walking distance, or particle movement, you can say in this case, because it's a particle. So just to break this up so you can see what we're working with, I've written it all out here. To evaluate the first one from 0 to 2, we plug in 2, 2, and 2, and we subtract when we plug in 0, 0, and 0, which just becomes 0. So this whole bracket here just becomes this whole little segment here. That's our first part. When we want to subtract off from 2 to 6, this little portion here becomes this little bracket here, where we plug in, again, everywhere you see a t, you plug in 6, 6, and 6, and whenever you see a t, you plug in 2, 2, and 2. And then the third bracket here is when we're evaluating it from 10, so 10, 10, 10, to 6, 6, and 6. So that's our last little step there. So I've written out all the work here so you can take a look at it. I think all my signs are right, and it looks about right. This is the area that will be between 0 and 2. This is the negative area between 2 and 6. And that's the area between 6 and 10. So because you're subtracting the negative, you end up adding. So you end up with 64 plus 160, so 224. And again, your units are going to be in meters, because this is the amount of distance you've actually traveled back and forth during that time.